If we apply all this understanding to boiling in a fire tube shell-type boiler, then we can draw the following conclusions. During starting conditions, the third pass observes the natural convection boiling until steady-state conditions are achieved, whereas the furnace and the second pass observe nucleate boiling until the steady operating conditions. Once the steady state is reached, the third pass of a well-designed boiler tends to maintain nucleate boiling, stage 2, where the heat flux closest is to critical heat flux, providing the largest surface area in this pass, thus optimizes the performance of the boiler. The second pass is dominated by transition boiling, resulting in lower heat flux, with heat flux increasing as the flue gas and wall temperature reduces towards the end. The furnace wall temperature is the highest among all heat transfer surfaces in the boiler. This means that the furnace will always host film boiling with the radiative heat transfer being dominant. The furnace wall must withstand high compressive stress due to water pressure at a very high temperature. This often necessitates higher thickness, and in some cases, ribs need to be provided to protect the furnace against thermal stresses as well as creep.
Fluctuating operation. During regular operation, the steam demand from the boiler can change over time, leading to a fluctuating boiler operation. If the steam demand reduces, the steam pressure tends to increase because the burner is still operating at the previous load conditions. Above the safety cutoff pressure, the burner is automatically shut off to prevent pressure overshoot for steam. In other words, the boiler is tripped. In this case, the flame and the flue gas temperature as well as the corresponding wall temperature for the furnace section reduces suddenly in the boiler. This means that the T excess also reduces corresponding to the furnace wall temperature. However, the heat flux during this reduction in T excess remains constant, deviating from the pool boiling curve. This means that the steam generation will continue for a few seconds even after the flame is turned off. When the steam demand increases again, the boiler pressure drops and the burner re-establishes the flame. Consequently, the furnace wall temperature increases, leading to steam generation, and the steam pressure stabilizes again to optimum levels. In this case, the pool boiling curve is followed without deviation, and the heat flux reduces to Leidenfrost point and increases again into the film boiling region. This means that the steam generation will take a few extra seconds to re-establish to the desired levels. Both these effects necessitate that the water level in the boiler as well as the safety cutoff pressure are carefully designed and controlled. This ensures that the boiler operates within the safety limit. Moreover, it also ensures that the stored steam above the water level inside the boiler is sufficient to adjust to the steam demand fluctuations as well as the resultant variation in the pool boiling phenomenon.
Thus, all these phenomena from different thermal as well as mechanical sciences create a complex and wonderful interplay in a fire tube boiler to achieve the seemingly simple task of generating steam